Hello everyone. I'd like to talk about forward and inverse kinematics now. And I'm going to start with a demo that you can get to. It's under class exercises on the class webpage for kinematics demo. I'll provide a link in the description. But so what I want to start to talk about now is how to control skeletons. And so here's one of the simplest examples I can think of. So if I had this skeleton here, where it consisted of 3 bones and 4 joints, that's the terminology for it. And I'm going to fix this joint here, the one that's highlighted in red, that's called the base. And then this joint in green is called the end effector. That's the thing where I can actually reach to some kind of target. For forward kinematics, what I do is I choose a rotation for these at these different joints. And it's really just like a scene graph. So if I rotate the first angle, let's say 30 degrees counterclockwise, then it rotates certainly the bone under it, but also all of those bones go along with it. So this one's like at the top of the scene graph, and then we rotate and then translate to get to the next bone. Actually, I guess technically you would want to translate first, then rotate. Okay, but anyway, just like a scene graph, I can do something relative to the next node down in the scene graph, and I can say, okay, well, what if maybe I want to rotate this by negative 45 degrees or something? So that'll do that, and it'll rotate everything under it by negative 45 degrees, and then of course I could go to the next one, choose to do some kind of different rotation there, maybe rotate that 90 degrees counterclockwise. And so yeah, just like a scene graph, the thing at the top, if I change it, it moves everything underneath, right? So see how it moved everything underneath. And if I do something in the middle, that moves everything underneath it in the middle there. So that's all there is to forward kinematics. We already know it. It's just like scene graphs, but applied to this situation of a skeleton with joints and bones. Okay. But now the question is, can we go the other direction? So in other words, we want to solve an inverse problem where if I want to reach to some particular target. So let's say that I put this black pixel, let's say that I put it here. Can I figure out what transformations to apply at each joint to get this skeleton to where the end effector reaches that target? So I had us play around with this in class. I'll just do it again here myself. But yeah, if I play around with this a little bit, let's see if I can get down there. I'm probably not doing as well as my students were, because they did pretty well. But the amazing thing was, people actually, everybody came up with a slightly different solution. So, okay, I'm just going to play around with this for a second and spare you. Okay, so I played around with this a little bit more, I adjusted the angles, and I eventually got it into a configuration where it reached the target. Now, if there is a solution, there may be infinitely many ways of doing this. And again, as we saw in class, everybody came up with a different way. So in general, I mean, this you can solve this as an optimization problem, where the variables are, the angles that you're going to put in here. You solve for those variables. The objective function is the distance of your end effector to the target, and then you just try to minimize the objective function. But there's actually an even simpler way of doing this called FABRIK. So let me tell you what this. It's a very cute but confusing name for this, because fabric, it sounds like cloth, which actually is another topic in graphics. But this FABRIK stands for forward and backward inverse reaching kinematics, or reaching inverse kinematics. Okay, so this is an algorithm to solve. So given a base of a skeleton here, so this is the base, let me just label that, and then given an end effector, I want to figure out how to move these joints without stretching them, so that the end effector reaches a particular target. So maybe I'll put the target over here. And let me draw that red just to be consistent with what I was showing a moment ago. So this is the thing that I want to reach. So this is my target. Oh, okay. And so FABRIK doesn't actually do an optimization problem directly. It instead just uses some kind of geometric heuristics to do something very simple. So what FABRIK does is it says, okay, let's start at the end effector. And let's just pretend for a second, let's cheat, and we're going to yank this out of its socket and drag it over to the target. Obviously, that I haven't solved anything because I'm not supposed to do that. I'm not supposed to stretch the bones or anything like that. But what I can do though is kind of work backwards here, hence the name. So first I'm going to work backwards and say, okay, if I yanked that out, what can I do to kind of fix that up a little bit so that if I look back here along the line to the joint that I just yanked it out of, what if I were to put it back on that line? So I'll show you this here. If I, oops, I didn't mean to stretch it. If I keep it as is, but I start to rotate it clockwise here. So you see, I'm not changing the length, but I could sort of reach back towards that joint that I just yanked it out of. So basically what I want to do is I just want to construct a vector with the length of this joint here. So the length is d4. So construct a vector of length d4 that points from the new position of this end effector in the direction of the joint that I just yanked it out of. Okay. So now I'm going to repeat that process. So now I'm going to, okay, I wasn't able to reach all the way there. So now I'm going to pull out this joint, D. I'm going to pull that joint out along with the bone. I'm going to yank that out and pretend that I was able to, it's always hard to make the right selections in Inkscape here. Yeah, so pretend that I was able to put that exactly where I wanted to. So I put that here. And then the same kind of thing. Okay, so this is where this joint D showed up. I really want it to reach towards the joint that I just pulled it out of. And so what I can do is, again, I want to put this in the direction of C, the thing I just yanked it out of, but without stretching it. So I want to keep it the same length. And in code, you don't actually rotate this. I'm just doing this for illustration. Again, what you do is you construct a vector that starts at D, goes in the direction of C, but it keeps the length of the bone from C to D, which that length here is D3. Okay, so it ends up here, and it reached a little bit past where C was. And so I just keep going. All right. So now I yank C out of its socket. So let me do that. And okay, got him. I yank C out of its socket. Oh, come on! I almost had it. Yank C out of its socket. Looks like I keep selecting that by accident back there. Give me 1 second. Okay, there we have it finally. So I yanked C out of its socket. And now I'm going to rotate this towards B, right? So I'm going to construct a vector from C. So I might as well draw that line again. So from C in the direction of B, I want to construct a vector that has the length of the bone. And so you see, actually this is kind of interesting, that this often happens. We basically almost got it. But this might not be 100% there. If I get rid of the fill here, you can see, okay, maybe it's not quite on center, so technically I have to keep going and actually yank B out of its socket here, yank this bone out of its socket and move this up ever so slightly, right? And eventually I'll end up at the root. Now the root's not supposed to move. but maybe it does. Let's just say for the sake of argument, the root moves like a little bit. Okay, in the process of doing this, let's say I move the root, right? So I follow that process all the way back, but then let's say maybe the root moves like over here or something. Amazing! I almost solved this already, actually. but let's say that the root moved a little bit. So now what we need to do, so now the root moved, but the end effector was correct. What we need to do is this whole process again in reverse. So now we pretend that the end effector is the base, and that this is the end effector. So now we're going to yank this out and put it where it should be at the root, and then follow that whole process in reverse. So it's probably better at this point if I just show an animation, because it's the same exact thing but going the other way. Okay, so here's a little demo I made. I should mention actually this is from a fairly recent paper by these two authors. So yeah, 2011. It's really not that old in the lifetime of graphics. So anyway, I've implemented this here. It's going to be your job to implement it in the homework. So actually, I mean, it works really well. So let me select another target. Maybe I'll put it over here. So the first time I went forward and backward, so I went forward, it probably was a little bit off of the base, and then we put the base back and ran it this way, and it ended up slightly away from the target. If I do one more iteration, it gets much closer, and then we're basically there. So you only have to do a few iterations back and forth, and it will reach the target, usually. So that one, yeah, I just had to do 2 and it was there. Now, if I put the target, so maybe I'll make this arm a little bit shorter. If I put the target out of range, it'll end up just reaching as far as it can, and in the direction of the target. But yeah, so that's it. So what I want to do now is I want to challenge you to implement that in code. That's going to be what you're doing on the third homework. So you're going to implement this to get this skeleton to reach towards different things. So what you do in the homework, actually it's a little bit different, because here I already have just a linked list, just like a line of joints. When you have a skeleton, it could be have a more complicated tree topology. And so what you'll do is choose a particular joint that's at a leaf of the tree, and you'll trace back until you get to a joint with multiple children, and you're going to treat that as the base. We actually call that the subbase. So that's what you're going to do in this assignment. So you can implement FABRIK, and then you will use it to animate and actually pull the entire mesh along with the skeleton, which is the next step called skinning that I'll explain in a moment. Okay, but that's it for FABRIK for now.